All right, so welcome to another lovely day here in Calculus World. The plan today is to talk about limits at infinity, what it means when we want to look really far away, either in the x or y positive or negative x direction. So we're going to talk about that and then kind of put this together, all together with increasing and decreasing, concave up and concave down, and other stuff that's not that we're just going to put that all together so we can get really, really good graphs of functions with no technology really. So that's the goal for today. But as always, before we go there, are there any homework questions or questions about what we were talking about last week that you'd like to talk about? All right, well, hearing none and seeing none. Oh, that was a premature call. Ollie just typed in that she's finding the number she wants to see. All right, so number 8 from 4.4. We can do that. All right, so let me go ahead and share my screen. All right, so hopefully everybody can see 4.4 is opening up here. All right, so let's go look at number 8. All right, so we've got a function, f(x) equals 1 minus 5x squared on the interval minus 5 to 6. So it says find the average or mean slope of the function on this interval, i.e., all right, so they basically gave us the quotient, the difference quotient form there, but that's just slope.
I'm not sure this is the problem I was talking about. I think this is maybe number 1 at the top there.
You're right, it does say number 1. Sorry about that.
That's okay, thank you.
Okay. So at 10:17 a.m., you pass a police car at 55 miles an hour, stopped on the freeway. You pass a second police car at 55 miles an hour at 10:53, which is located 39 miles away. If the speed limit is 70, can the police cite you for speeding? Okay, so basically we need to answer this question. We need to first figure out your average velocity from 10:17 a.m. to 10:53 p.m. I think that was an error. I think that's supposed to say a.m. so that it matches this time. But so we've got a difference in time, right? We can figure out how long we've been driving, and we also know how many miles we've gone. So we can use that to figure out miles per hour. Okay, so we're going to start by just figuring out what was our average speed. All right, and then we're going to then we'll answer these other questions. So let's do this first. Let's figure out what our average speed was. So let me just write down some numbers here. And we'll go to the whiteboard. All right, so at one point, we're here. This is at 10:17 a.m. And then a little bit down the road here, I'm going to go 39 miles. We're back here again. at 10:53 a.m. Okay, so if we want to get our speed, it's going to be the distance divided by the time. That's just good old, I call it the dirt formula, distance equals rate times time. But another way to remember this, if you have trouble remembering this formula, is just think about the units we use. It's miles per hour, so it's distance over time. Okay, so we're going to go 39 miles. And in terms of our time, well, we know what the difference is in minutes, right? That's going to be, what, 36 minutes? But 36 minutes doesn't really help me. I want it in hours, so we can convert this. It's 36 over 60, which is 0.6 hours. So we travel 39 miles in 0.6 hours. All right, so let's do the division on that. Let's see, it's going to be 13 times 5. So that should be 65, I think. Okay, so there's going to be the answer to the first part of the question. Our average speed over that interval was 65 miles per hour. All right, so before we go and answer the other parts of the question, we all good with this? Any questions on how I got this? All right, my only advice, be very, very careful with units. All right, make sure you've got the units what you need. So if you have to convert, like we did the 36 minutes to 0.6 hours, make sure you do that. Okay, so now let's go back to the question and let's answer the remaining parts, right? Because we know our speed. We just calculated that was 65 miles per hour. Okay, so by the mean value theorem, since the average velocity over the interval was, let's see what our choices are here for selecting the answer. Oh, nice and easy, less or more. So the average velocity, was that lower or higher than the speed limit? Well, the speed limit was 70 miles an hour. So we are actually less than that. Then the police can or cannot cite me for speeding. Well, the answer to this one's going to be cannot. There is the potential that I was going over 70 miles an hour at some point, but they don't know that, right? You think about the information they have. When I passed them each individually, I was going 55 miles per hour. So I definitely wasn't speeding at that point. And on average, I was going 65. So they know at some point I was going 65 miles an hour, right? Mean value theorem says there's a moment where our instantaneous rate of change is the same as our average. So there was at least one point in which I was going 65 miles an hour, but they don't know anything else, right? There could have been a time I was going over 70, but they don't know that. All right, so I think we're good. Let's check our answer, see if I get a green box. Yes, got it. Green check marks all around. So obviously yours will have different numbers, but this is the process. All right, so Alia, is that good? All right, thumbs up, I like it. All right, any other homeworks before we move on? All right, cool. So don't forget that there is homework due tonight. I believe it's 2 sets. Just make sure you get those done by midnight tonight. All right, well, with that, I'm going to go hop over to the whiteboard and we will keep talking, drawing graphs of functions. All right, so up to this point, we've seen how calculus can help us get graphs of functions. We've done the first derivative, giving us ideas of extrema, maxes and mins, things like that, increasing and decreasing. The second derivative, we've been able to find concave up and concave down. So whether it looks like it fits on a cup or on a frown, and also inflection points, those places where we change concavity, right? So today we're going to start with what happens when we go far away. What happens when we look out really, really far down the x-axis? What's going on with our function? Or going the other direction, right? If we end up going to the left, what happens when we go really, really far that way? So I call this end behavior. So you hear me talk about the end behavior of functions, and that's what I'm talking about. But mathematically, what we're doing is we're looking at infinite limits. So infinite limits are very much like limits that you know. The idea is what's happening as we approach a number, right? That's the idea of a limit. But an infinite limit is what's going on as our x's grow without bound. I'm going to write here the limit as x goes to infinity, or the limit as x goes to minus infinity. Okay, so this is what we're going to talk about when we talk about an infinite limit, is what happens as we go really, really, really far to the right, or what happens as we go really, really, really far to the left. Now, this is a little bit different than what you're used to, because with infinite limits, or with regular limits, we are always approaching a number, right? We are approaching a specific value. We just never quite got there. Excuse me. Well, infinity is not a number. There is no place on the real number line that's infinity, right? Infinity is just a keep going. So in that sense, it's a little bit different, but it's the same as in the other limits where we don't get to infinity. There's no such thing as plugging infinity. But what we're looking for are trends. Okay, what's the trend of this function? Is there a number that it's approaching when we go really, really far out there? Okay, so it's still got that same kind of idea. So let me show you the technical definition of the limit. Okay, so we say that the limit as x goes to infinity of f of x equals L. So there's some number. What this means is that for every epsilon, yep, our friend epsilon's back. For every epsilon greater than 0, there exists an m greater than 0 such that the absolute value of f of x minus L is less than epsilon when x is greater than m. So I'm going to give you a second to write that down, and then we'll talk about what that means. Okay, so our friend epsilon is back, but you may notice there's no delta. right? There's no delta here, but we have kind of the same thing going on. Epsilon was a vertical distance away from our limit L. So it was forming a little strip. And what we needed before with our function is, or with our limit is, as we approached C, we had to make sure our function was entirely in that strip. Okay, well, the same thing's happening here. We're still creating a strip. This line where it says the absolute value of f of x minus L less than epsilon, that's creating that little strip. And our function has to be in that strip. But notice what this is saying is that it has to be in there once we get past some point M. So graphically, what's going on? Okay, we've got our function doing whatever out here. I don't really care about that. I care about far away. But there's a value L, that is our limit. And we're going to go plus and minus epsilon. So we create our little strip like this. And what this is saying is that no matter what that epsilon is, there's going to be some place out here, we'll call it M, that once we're beyond that, our function lies entirely in this strip. Okay, so what we're going to see in terms of a function here, maybe this is our function. Okay, so it does this. Notice that as we keep moving far to the right, this thing starts getting closer and closer to L. L is right smack dab in the middle of this strip. But eventually, there's a place at which all of the function lies in that horizontal strip. And in fact, let me redraw this so that it matches my graph. The M in this case would be right here. Because to the right of M, our function is always within this epsilon strip. All right, we're going up and down epsilon from L. And so you start making epsilon smaller, you make this strip smaller. I might have to move further away. I might have to move my M down the line as well. But if this limit exists, there's going to be some place where eventually, once I go beyond that, I'm always within that little horizontal strip. So you can probably see this, I hope you see the similarities to what we are doing with regular limits. It's just now we're not approaching a point, we're just saying that eventually. Infinite limits are all about eventually. Eventually, our function gets close to L. And you can tell me how close you want me to get to L, and I'll tell you, okay, eventually, once you get beyond this point, you're always going to be that close. So this would be one for positive infinity. For negative infinity, hopefully you can see that the only difference is, since we're flipping it over, is that there's going to be some M where we're within that strip once we get smaller than M. Okay, so let me go ahead and write that up though. If it was a minus infinity, so limit as x goes to minus infinity of f of x equals L, the only thing that changes here is that it would be x is less than M, and there's some M less than 0. Now we need to be negative somewhere out this direction. And then once we get past it, meaning less than M, we're within that strip. All right, so that's the idea behind these infinite limits. So there's a value that we get to eventually, or we get really close to eventually. All right, now when we have one of these things, this guy L, we actually call it a horizontal asymptote. So you already know about these. right? You know about line, horizontal, or asymptotes in general are lines that we approach. We've talked a lot about vertical asymptotes. Horizontal asymptote is the same kind of idea. And there's going to be a horizontal asymptote at y equals L. So whatever that limit is, that's where we're going to get a horizontal asymptote. So you can probably see why this is going to be helpful when it comes time to drawing graphs of these things, is because this is giving us some end behavior. It's telling us what's happening as we go far away. All right, now, these limits don't always exist. There are lots of functions that don't have a limit as you go to infinity. Just like there are lots of times when we tried to take regular limits as we're approaching a point and they didn't work. Same kind of thing can happen here, right? Like think about some of the issues we ran into before taking limits. We had different values from opposite sides. We had vertical asymptotes. The function wasn't even defined there, right? Things like that. We can have similar issues here. Now, the two different values from the two different sides is never going to be an issue because there aren't two sides to these anymore, right? The limit is we go to infinity. There's one direction that we go towards infinity, only when we go to the right. Or if we're going to do an infinite limit, but to minus infinity, there's only one direction to go. Come here to the left. So we don't have to worry about that. But we do have to worry about the infinite. It is possible that as we go really far away to the right, that our function continues to grow up or down. You've seen so many examples of those that I don't even really probably have to show you any. But think about just a line, right? Think about a line. A line is never going to level off unless it was horizontal in the first place. But as long as it's not a zero slope line, yeah, you can keep going forever and you're going to keep going up. It's got positive slope, or you're going to keep going down. So lines are a great example. Any polynomial actually has that kind of thing going on. Exponential functions grow without bound. Logarithmic functions grow without bound. Some of the trig functions have different issues. Like sine, there is no horizontal value. There is no infinite limit because it keeps bouncing back and forth. And we saw examples of that with regular limits as well. So all of those same issues happen. Ollie, hold on. So is your note on the left that this graph, what this means is that if an infinite limit exists, there is a horizontal asymptote at y equal L. And this graph would be one of them. But any function that has an infinite limit has a horizontal asymptote at y equal L. That makes sense?
So it's not bouncing above it and below it to the right of M?
I'm sorry, can you say that again? I didn't turn up my volume.
It's not like bouncing above it and below it once it's to the right of M. Is that right?
Okay, so bouncing above or below is actually okay. With horizontal asymptotes, you can cross them. So what has to happen is that even if you're bouncing above and below it, you're getting closer and closer to the asymptote as you move further out. So for example, if I were to draw this picture, so let's say that this is a horizontal asymptote, I could have a function that does this. Right, that just kind of keeps oscillating back and forth. But notice that those oscillations get smaller and smaller and smaller. This is still a horizontal asymptote because as we go towards infinity, as we go far away, we get really, really close to that line.
Is that true with vertical asymptotes too, or is that just a horizontal asymptote thing?
just with horizontal. Vertical asymptotes you never cross. Because think of it, there's a difference. There's a huge difference between why we have vertical asymptotes and horizontal asymptotes. They're still asymptotes, they're still lines, but there's a huge difference. What has to be true about a function for us to get a vertical asymptote? I don't know, maybe you never thought about it.
It doesn't exist at that value?
Yeah, the function doesn't exist there. Right? Those were the things that led to like division by 0. But the function never actually existed. And that always had to be the case if there was a vertical asymptote. Now, the horizontal asymptote, we're not saying that the function doesn't exist. Right? The function definitely exists. We're just saying that no, as we move far away, we get really close to it. So here's the deal with asymptotes. Asymptotes are lines, no matter how they are, whether they're vertical, horizontal, or even if they're slanted. Now, I'll show you an example of one of those in a little bit. But it doesn't matter how those lines are. The idea behind an asymptote is that we get really, really close to it as we move far away. Okay. For the vertical, think about that. We get really close to vertical asymptotes. We never touch them, but we get really, really close when we move far away. Far away now, though, is up and down. Right? So for vertical asymptotes, we're moving far away up and down. But as we move higher or lower, we get closer to that line. Now with horizontal asymptotes, everything gets turned. Now we're moving further right or further left. And as we're moving further away, we are getting closer to that line. Crossing a line is close, right? Like if you're on that line, you're not just close, you're really close. So there's nothing to preclude crossing it. It just has to be, that's what we get close to when we move far enough away. But vertical asymptotes are different. We can't cross those because our functions aren't defined at those points. So when you hear asymptote, don't think of, oh, it's a line I can't touch. That's not accurate. It's a line that we get really close to. So does that help? All right, I see a thumbs up. I like that. All right, so for horizontal asymptotes, like I was saying, or for infinite limits, they don't always exist. There isn't always this kind of a number that we get. Just like regular limits didn't always exist. So we have to realize that there's still going to be issues where we don't get infinite limits. But it's pretty clear from structure what they look like and how you can figure that out. The one thing I do want to mention is that often what we're going to get are infinite limits for our infinite limits. We're going to get a limit as x goes to infinity of minus infinity or positive infinity, meaning that they either drop without bound or grow without bound. And so it is quite common for us to write, even though technically this isn't super good, you will still see us write sometimes like the limit as x goes to infinity of f of x equals, say, like minus infinity. So you remember when we did this before, as we were approaching a point, if we got negative infinity or positive infinity, that meant we were dropping or climbing at that one point, which led to vertical asymptote. Now, it doesn't mean that it's going to be a vertical asymptote. It just means that it never stops dropping as we move further and further away. So something like this would mean our end behavior is, yeah, it's just dropping as we go to the right. Or sometimes we might have limit as x goes to positive infinity of x equals, again, positive infinity. Well, that's going to be one that grows forever. So you've seen lots of those. We're going to continue to see lots of those. Like, again, think polynomials. And that's what we're going to write to let us know what's going on with the end behavior. Because it's just fast. It's a simple way of writing something with symbols instead of huge strings of words, and mathematicians are lazy, right? I can get my point across really easily by writing. All right, so I guess the next question is, well, how do we find them? How do we figure out what these limits are as we go towards infinity? So I'm going to start you off with an easy one, a real basic function. And let's talk about this guy. Let's look at the limit as x goes to infinity of 1 over x. So nice simple function. It's a butterfly function. We already know a lot about it. And so the question is, what is the limit as x goes to infinity? Now, we can start in very much the same way that we did other limits by just plugging in numbers. You remember doing that? Hopefully you remember. Something like if we're going to say the limit as x approaches 1, we put in 0.9, 0.99, 0.999, right? And we looked for a pattern. We can do the same thing here. It's just now if we're going to start plugging in numbers, we need to plug in big numbers. So we're going towards infinity. And we want to keep plugging in bigger numbers until we start seeing a pattern. So for example, plug in 1,000. 1,000's pretty big, right? So we plug in 1,000. Well, what do we get if we plug in 1,000? So if we said we got f of x equals 1 over x, let's make a little list here, some x's and some y's. So we plug in 1,000, we get 1 divided by 1,000, which would be 0.001. Okay, well, let's go bigger. Let's go further towards infinity. So I'm going to jump up from 1,000 to, how about we do 1,000,000? That's a pretty big number. It's way bigger than 1,000, right? So 1,000,000, man, we're way down that line. Well, 1,000,000 is going to give us 0.000001. I did my count on my zeros right. Okay, so that's what we get if we plug in 1,000,000. So 1,000,000 is really big, right? It isn't. 1,000,000's small. In terms of infinity, it's not even close to infinity. So how about instead of 1,000,000, let's go 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, let's go with that number right there. 1 followed by 12 zeros. All right, that, my friends, is a trillion. So like when they talk about national debt in trillions of dollars, yeah, that's what we're talking about. Big number. Okay, well, if I do 1 divided by that number, I get, give me a second here, I need to count. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15. Oh, no, wait, too far. Only 12 zeros. 1, 2, 3, 4, 5, 6, 9, 10, 11, 12. Okay, so we get 0.00000000000001. All right, so do you see a pattern here? What's happening to this number as we go further down the line?
Gets smaller and smaller.
Getting smaller and smaller. What's it appear to be approaching? Can you give me a number?
0.
Yeah, about 0. So it definitely looks like the limit as x goes to infinity of 1 over x is equal to 0. Okay, now that's what it looks like. It feels good, right? And we've seen that that's usually good. but sometimes we get screwed over when we go with B. Yeah, it feels good. But let's think about the definition of the limit. So the definition of the limit says that give me an epsilon, tell me how close you want me to 0. I'm going to be able to find a place where once I get beyond that, I'm going to be within your tolerance of epsilon. And hopefully you can see that that will definitely occur, right? You tell me you want to be within epsilon. I just have to go out beyond 1 over epsilon, right? So if your epsilon is 0.1, I just got to get beyond 10. You want epsilon of 0.001, I just got to get beyond 1,000 and so on. So no matter how close you tell me to get, I'll eventually be able to get there if I put in a large enough number. Okay, so this limit definitely does equal 0. And if you remember your graph of 1 over x, you can see it. 1 over x is the butterfly function, and so it looks a little bit like this. And you can see that as we move in this direction, as we move towards positive infinity, those y values drop and they get closer and closer to 0. Okay, so this function right here, 1 over x, it's pretty easy to see that its limit does equal 0. Okay, so we can follow this process for any kind of function. Start plugging in numbers, bigger and bigger numbers, shoot for looking for the pattern, see what we get. But you can see that this is kind of cumbersome, especially if this function is a little bit more complicated. But we can actually make use of 1 over x to help us figure out limits of other functions. So for example, what if I wanted the limit as x approaches infinity of 3x cubed minus 2x squared plus 1 over minus 6, or how about we'll do it this way, 6 minus 6x cubed. So there's a function that probably none of you can visualize what it looks like. At least that's my hope. I have no idea what this looks like. But I still want to know what happens as I go towards infinity. Okay, now comparing this one in green to just good old 1 over x, they probably feel completely different. You might go, well, that's great. That doesn't really help me at all. But what we can do is actually do a little bit of algebra on this guy and turn it into a form where we can use what we just saw with this 1 over x business. So here's what I'm going to do. I'm going to take the top and bottom of this fraction, and I'm going to multiply by 1 over x cubed. And this is completely legal, right? Anytime you have a function, you can go ahead and multiply top and bottom by the same thing, as long as it's not 0. And 1 over x cubed never equals 0. It gets close, but it's never actually equal to 0. So this is totally legit. Now, what this allows me to do is to distribute through to each of the pieces, and I can cancel out some of the x's. So what I'm left with here then will be the limit as x goes to infinity of 3 minus 2 over x plus 1 over x cubed divided by 6 over x cubed minus 6. So that was just a small little algebra step. And it turns it into this form. All right, but at this point, you're probably thinking, okay, Bruce, great. So what? What does this do for us? Well, check this out. Now we can go back to the limit rules. Remember the limit rule. So if we had a fraction, we could evaluate the limit of the top and bottom separately. When we have addition and subtraction, we can evaluate each of those limits individually and add them or subtract them. Right? So we have all those kinds of rules. If we have a constant multiple, the constant multiple just keeps going. But what this is going to let us do is now evaluate these individual limits. So let's think about this. What happens to 3 as we go to infinity? Well, 3 stays 3. 3 doesn't change. It's always 3. So that's going to equal 3. Okay, what about the 2 over x? What's going to happen to that as x gets really large? Good, thanks, Eris. It's going to be 0. Why? Well, because 1 over x went to 0, so multiplying by 2 is still going to go to 0. Plug in big numbers, that's eventually going to drop off. So that's going to be 3 minus 0. All right, what about the 1 over x cubed? Well, yeah, thanks. I was about to say, Eris just hit enter again. It's going to go to 0. It's just going to go to 0 faster, right? I'm going to take a really big number and cube it. That's going to be an incredibly large number that I'm dividing into 1. That's going to go to 0. So not just does 1 over x go to 0, 1 over x squared goes to 0, 1 over x cubed, 1 over x to the 4th, 1 over x to your favorite number bigger than 0. Those are going to drop 0. All right, so on top, we're going to get 3 minus 0 plus 0. If you go to the bottom, same story. 6 over x cubed, that's going to go to 0. And the 6 is going to stay a 6. So we get 3 over minus 6, which is negative 1/2. So what we know is that as we go towards positive infinity, we get minus 1/2. All right, so Eris just said, so you could just look at the leading coefficients. Yeah, and you probably remember that trick from pre-calc at some point when you're trying to find horizontal asymptotes, and you're always told, hey, look at the leading coefficients. Leading coefficients meaning the numbers on the highest power of x. And you could use that to find the horizontal asymptotes. So that trick that you learned in pre-calc, this is the actual math behind it. This is why you could do that trick back in the day. You didn't realize it. You were basically just told, hey, just do it this way. But this is why. This is why it works and why you're allowed to do that. So if all of a sudden you just went, whoa, I have no idea what he's just talking about, let me remind you of that little bit of algebra trick when we have rational functions. So fractions of polynomials. So this is what I do when I'm trying to find infinite limits. I don't actually go through the whole process because there isn't a point, because there are patterns. And so here's what you want to look for. All right, so this is going to be for rational functions. Okay, so rational functions like this guy right here. Again, rational means polynomials divided by polynomials. All right, so if the degree on top is greater than the degree on the bottom, so you've got a higher degree on top than on the bottom, so like an x to the 4th over x squared, or an x to the 7th over x cubed, or something like that. What we know is that the limit as x goes to plus or minus infinity, so whichever way, plus or minus infinity, is going to equal plus or minus infinity. So if the degree on top is bigger than the degree on the bottom, it's going to either grow without bound or drop without bound. And that's why I put plus or minus, because I don't really know which one it is, but I do know that it's going to have in behavior that is unbounded. So it's going to go forever. Okay, so if the degree on the top is bigger than the degree on the bottom, you can just write that, well, in terms of which way, plus or minus infinity, that's where you do want to plug in a number and just see, do I get a positive or a negative value? Okay, so then the second possibility is if the degree on the top is less than the degree of the bottom. Okay, so that's going to be, now we've got an x squared over an x cubed or something like that. This time, your limit as you go to plus or minus infinity is equal to 0. Always. Okay, so if the degree on the bottom is bigger than that on the top, your limit's just 0. So this then, of course, leads us to the third option, which is what if those degrees are equal? Right. So what if the degrees are the same? And that's what we just saw with that example with the x cubes. There was an x cubed on top and bottom. What you do is you get the limit. And again, this is plus or minus infinity. Doesn't matter which way we go. It's going to equal L, where L, this is the ratio of the leading coefficients. So if you look at that example that we just did, we had a 3x cubed on top. We had a minus 6x cubed on the bottom. So you take the ratio of those, 3 and minus 6, and you get negative 1/2. Let me show you another example. Since I erased that one and I can't really go back and point to it. Let me show you another example here where that happens. So let's look at, say, the limit as x goes to minus infinity of 5x to the fourth minus 3x cubed plus 2x plus 1 over 2x to the fourth plus x squared minus 4x plus 2. Okay, so here is a ratio, a rational function. Looks like this. So we look at the degrees. So on top, we've got degree 4. On the bottom, we also have degree 4. So we're in this case where the degrees on top and bottom are the same. So what we can do is actually just look at those leading coefficients, 5 and 2. And so this tells me that this limit is equal to 5/2. Done. So with rational functions, it's actually pretty quick and pretty easy, because all you have to do is look at those highest powers and look at the coefficients on those highest powers and form your ratio. All right, so if you remember that trick from pre-calc, cool. If you don't, well, now you've seen it. And there's definitely math behind it. It's using the fact that 1 over x or 1 over x squared or 1 over x cubed or 1 over x to your favorite power there, as long as that power is positive, those things drop to 0. Okay, so nice little trick to help you find these horizontal asymptotes. We'll talk a little bit more about what happens if the degree on the top is bigger than that on the bottom, because sometimes that gives us some more information that we can use. Because just jumping straight to the limit's infinity, yeah, but maybe if we know a little bit more how it's going to infinity, that can help us. But I want to show you a couple of other kinds of functions that give us infinite limits that require a little bit more thought or a little bit more work. Okay. But before I go there, questions on this? What questions do you have that I can answer? All right, I'm seeing none, so I'm guessing we're doing okay. All right, well, let me show you another function. And this time, let's use a radical. Let's throw a root in here, but we're still going to make it a fraction function. So let's make this one x over the square root of 9x squared plus 4. And so my question here is, what happens as we go towards plus or minus infinity?
It still goes to 0.
All right, so it goes to 0. Why do you
Wait,
say that?
I think it might go to I think it might go to negative infinity.
Okay.
Because it's a square root.
All right, so because originally you said 0.
And then I thought back about it because you cancel, you can take the 9x squared out and the 4 turns into a 2.
Okay, so you originally went to 0, and I'm going to guess because you thought, all right, I've got a degree 1 on top, I got a degree 2 on the bottom, and then because of that, it'll go to 0. But that was a good catch of saying, no, that's actually not the right way to think about it, because while there's an x squared on the bottom, it's not really like an x squared, because we're taking the square root of it, right? So we have to be a little bit careful about just jumping straight to the powers, because square roots are actually powers as well, right? So we get some fractional stuff. So it's good that you caught yourself. So then you said you were thinking maybe it goes to infinity, but then you changed your mind again, and you said, what number did you say again? I don't remember.
Oh, I said negative infinity.
Oh, you went to negative infinity. Oh, because of the square root.
Yeah.
Okay. So clearly this one's going to behave a little bit differently. And we could plug in numbers like we did before. Plug in 100, plug in 1,000, plug in 10,000, plug in a bajillion, right? Whatever number that happens to be. You could plug in those things and look for a pattern, see what's coming out. Or if we are going to minus infinity, same thing, put in negative 100, negative a million, negative a Google, if you want, which is a real number, by the way, a Google. Spelled different than Google, the search engine. But I don't want to do that. Instead, I want to do algebra. So check out what I'm going to do. I'm going to do the same kind of trick that I did before, where I'm going to manipulate this, but I'm going to actually do this by factoring on the bottom. Think about that 9x squared. Let me factor out an x squared. So I'm going to get x squared times . So I'm going to get x squared times 9 plus 4 over x squared. Basically, I divided out an x squared from both of those pieces. So that little algebra step is totally legit. I didn't do anything funky in terms of algebra. But there's a reason I did this. Do you see why? Do you see why I factored out an x squared?
Because of the polynomial inside the square root.
All right, yeah, the reason that did prompt me to do it was the fact it's a polynomial, but there's a specific reason why I factored out x squared as opposed to x cubed or x to the 4th or x to the 5th.
Because it'll cancel with the square root.
Yeah, that's exactly it. I'm taking a square root of x squared. Well, you guys all know what happens when that occurs, right? If you take a square root of a square, they cancel each other out. And what I'm left with is x over x times the square root of 9 plus 4x squared. And it's pretty easy to see that I can now cancel those x's from the algebra. And so what I'm left with is 1 over the square root of 9 plus 4, oops, not x squared, 4 over x squared. So I've got 9 plus 4 over x squared. Okay, so this was just a little bit of algebra, got us here. But now, can you tell me what happens as x goes to infinity? What happens to this?
Reduces to 1/3.
Yeah, it just ends up being 1/3. Because as x goes to infinity, the 4 over x squared is going to go to 0, kind of like we saw before. And we're going to be left with 1 over the square root of 9, which is 1/3. So what we just found out is that the limit as x goes to infinity of x over the square root of 9x squared plus 4 is 1/3. So if you were to draw a graph of this thing, you would see that there is a horizontal asymptote at x equals 1/3. All right, let me show you on Desmos. Let me show you that we actually do get this same thing. All right, so let me just switch our view here to my screen. All right, so everybody sees Desmos here. All right, so let's go ahead and draw a graph of this guy. So we had x divided by the square root of 9x squared plus 4. All right, so do you see it? Do you see the horizontal asymptote of 1/3?
I think if you zoom in, we might be able to.
How about if I do this? Let me just draw the line y equals 1/3. So the blue line is that horizontal asymptote. Do you see the function approaching 1/3? Look over here.
Yes.
Right, it totally does, right? It's definitely approaching it. All right. Okay, but do you see another horizontal asymptote?
Negative 1/3.
Yeah, definitely looks like there's another one. And potentially minus 1/3. Let me type in y equals minus 1/3 here, and let's do another line. So that's the green one, but you'll notice that there is another horizontal asymptote of minus 1/3. It's just when we're going the other direction. Okay, so we were actually correct. Like if you look at what our limit was, we got positive 1/3, but if we had tried finding the limit as we go to minus infinity, we would have been wrong. Yeah, okay, well, let me go back to the whiteboard and let's talk about that. Because this is definitely true, 100% true what we wrote up here, that the limit is equal to 1/3. But by the graph, we saw that the limit as x goes to minus infinity of this was actually equal to minus 1/3. So this is a graph that actually has two different horizontal asymptotes depending upon which way we go. All right, now, why? Why did that happen? Why is it that we didn't catch it? What's going on here? Well, it's all because of that square root. Let's come back to the original function. X over the square root of 9x plus 4. Notice that this bottom, this is always positive. Square roots are always positive. They're defined that way so that they're functions. When we factored out that x, when we got to this stage right here, this guy is sometimes negative. Right? X can be negative. But when we pulled it out of the square root, that's where the violation happened. That's where we lost this information. Technically, if you pull out the square root of, you have a square root of x squared and you simplify it, technically, you need to put absolute values around that guy. This is total math lawyer, but needs to happen. You need those absolute values. Okay, so that's why we missed it. Now, I'm not suggesting that when you do this algebra that you put the absolute values on there. I'm not suggesting that at all. I never do. But I remember that. I remember that this bottom is always positive. So then look at the top. The top is sometimes positive and sometimes negative, depending upon which way we go. So when we go to positive infinity, we get a plus over a plus. That's why we saw a positive 1/3. When we go to minus infinity, we get a negative over a positive. And a minus over a plus is negative. And that's why we got the negative 1/3. So when you run into something like this, if you've got roots, you got to watch, just got to pay attention and recognize that the signs, the plus or minus signs, might be off, and you do have to watch out for that. Okay, but just go back to the original. Use the original to help you. Look at what are the signs on top and bottom as you go the different directions, and that will assure that you find them. Now, you didn't have to worry about that with rational functions, because rational functions, doesn't matter if you go to plus or minus infinity when all you're doing is taking powers. But radicals, we do have to watch ourselves. All right, so it is possible to have two different horizontal asymptotes that you go to a different value as you go towards plus infinity or minus infinity. Just depends on the structure of your original function.
I have a quick question.
Sure, go for it, Alia.
I was just curious, how did you get to the original 1/3 from 1 over the square root of 9 plus 4 over x squared?
Okay, so the 4 over x squared goes to 0. Yeah. When x gets really big, 4 over x squared gets really small and basically goes away. So that goes to 0, which leaves me a 1 over the square root of 9 plus 0, which is 1 over the square root of 9, which is 1/3.
So could you always evaluate those pieces within the square root separately from each other? I guess that's where I was confused. It just seems like you'd have to do the whole thing together.
No, you can do them individually, just like when we had fractions with a whole bunch of pieces that were being added and subtracted, because the limit laws that we learned, well, now way back in like September, those limit laws still apply here. And so we can do them inside individually. So I guess long story short, yeah, we can do this. And the reason is because of the limit laws from forever ago. All right, cool. I like seeing the thumbs up. All right, so there's another kind of quirky thing that can happen with these infinite limits. You can actually get 2, depending upon which way you go. All right, so let's look at one more of these that has a horizontal limit before we talk a little bit more about the infinite types. And so let's look at this guy. Let's look at the limit as x goes to infinity of sine x over x. So if that function looks familiar, it should. Sine x over x. We played around with that thing before. Specifically, we looked at its limit as we went to 0. The limit as x goes to 0 of sine x over x, that was equal to 1. Hopefully you remember that from back in the day. But now we're not looking as we go to 0. We're looking as we go to infinity. What's going on with this? All right, well, what's your hunch? What do you think is going to happen as x gets really big? Make a guess.
It goes on.
All right, so it goes on, you mean like goes up or down?
Yeah.
Okay, so it's going to be an infinite limit?
Yeah, either negative, depends if you plug in a negative x or a positive x.
Okay, but we're definitely plugging in positive x's because I'm saying a limit as x goes to positive infinity. So in this case, we're plugging in positive x's.
So
All right, so your guess, Susanna, would be then it's going to go to positive infinity?
either that or go to 0.
Okay, or it goes to 0. Well, those are very different things.
Okay, well, it's more likely that it'll go to positive infinity, but there's an asymptote.
Okay, so here's what I love. So Susanna's giving me contradictory statements.
Okay, it'll go to positive infinity. There's my final answer.
No. Please don't take this in a bad way. I don't mean it in any kind of a bad way. I just want you to think about what you said. You said it's going to go to positive infinity, but it has a horizontal asymptote. Like that cannot happen. If you have a horizontal asymptote, it means you have a finite value that you're approaching as you go to infinity. So you can't actually have both of those. All right, so just realize that mostly this is a teaching moment for everybody, just to remember what a horizontal asymptote means. That is a limit. That is the limit as we're going to infinity, which is different than a limit being infinite, because then we're either going up or down, depending on the sign, plus or minus sign. Okay, so I think Susanna is not quite sure. I appreciate the fact that you're giving me, you're giving me a guess.
Well, I feel like it has an absolute value depending on what x is. It has an actual value because you can calculate it. But if you're just leaving it at x, then there's no actual value.
Okay, so you're right. I mean, we can plug in 1,000.
Yeah, and you'll get a number. You'll get a positive number.
Exactly. Well, it's not always going to be positive though.
Well, no, I mean, if you plug in 1,000, I think the number is positive.
Maybe. I don't know. I don't know what the sign of 1,000 is. Because here's the deal. Like the bottom is going to be positive, no doubt, right? It's just x, so it's going to be positive. The top, though, sine of x is sometimes positive and it's sometimes negative. I mean, shit, sometimes it's 0, right? Because that thing bounces around. And so depending upon where we are, it might be a positive number, it might be a negative number. All right, well, think about this though. That top number, that sign, is always trapped between plus and minus 1. Right? I mean, there's a biggest it can be and there's a smallest it can be. And regardless of what that number is, I'm dividing by something incredibly large. Like let's go to 1,000,000. The sign of 1,000,000 is going to be somewhere between plus and minus 1. That I'm now dividing by 1,000,000, that's going to give me a really small number. So if we were just to start plugging in big x's and see what happens, it definitely looks like these are going to get small. So I'm going to put equals 0, but with a question mark on it. Because it definitely feels like they should be getting smaller. Now, this is kind of the same case as the one that I drew earlier that was kind of oscillating back and forth on that line. I don't you remember if you guys remember, Ollie asked me about that. And I was like, you know, is that okay and all that? And for a horizontal asymptote, that's totally fine. But it appears though that as we go farther out, that oscillation gets smaller and we get closer and closer to zero. All right, well, I want to actually prove it. And I'm going to do it this way. I know that the sine of x is going to be between plus and minus 1. And we know that. Sine of x is nice. Which means that the sine of x over x is always between minus 1 over x and 1 over x. All right, so far so good? You believe me? I'm not doing anything funky. Okay, so now let's look at the limits of these two. What happens to those as x goes to infinity? So what happens to 1 over x? What's its limit as x goes to infinity? All right, thanks, Bailey. It's 0. Right, this one goes to 0. What about minus 1 over x? Hey, Bailey, hit enter again. It also goes to 0. What's the difference between those? Well, we're going to 0 either from the positive side or from the negative side, but either way we go to 0. All right, well, now we know for sure that sine x over x also has to go to 0 by the squeeze theorem. Remember that guy? It's been a while since we've seen it. But by the squeeze theorem, I know that the limit as x goes to infinity of sine x over x equals 0. So squeeze theorem was if we've got a function that's always trapped between two other ones, and those two go to the same value, then the one that's in between gets squeezed, gets pushed to that same value. So I just share this one mostly to remind you about the squeeze theorem. It's kind of useful. But to also remind you that it's okay to have functions that are oscillating about the horizontal asymptote. It still has a horizontal asymptote. If you draw the graph of it, you will see it goes to 0. I mean, it looks like a sine wave. It's just the amplitude drops. And because the amplitude is dropping, we're getting inside that little strip eventually. All right, so there's another one that's got a horizontal asymptote, just got some different kind of behavior than the other functions that we've seen. All right, so let's talk a little bit more about the infinite limits. What happens when we're going towards infinity, plus or minus infinity, as we go to infinity? Because not all of those growths are equal. And in fact, sometimes with rational functions, we can get some pretty decent information about what's going on as we go towards infinity. Right? So here's an example of one. Let's just look at this function right here. We're going to look at the limit as x goes to infinity of 3x squared plus x plus 1 divided by x minus 1. So think about our trick. We look at the leading coefficients. And so we see on top we've got degree 2. On the bottom, we've got degree 1. And so since the degree on top is bigger than the degree on the bottom, the actual answer to this is that this is going to equal infinity. Now, I know it's either plus or minus infinity, and the reason I know that it's positive infinity is by looking at the signs. On top, if x is positive, we're going to positive infinity, then I get positive number on top, I get a positive number on the bottom, because a really big number minus 1 is going to be positive. So plus over plus equals plus. That's why that's going to infinity. If instead we did the limit as x goes to minus infinity of the same function, this time look at the leading terms and think about what their signs are going to be. On top, I'm going to get another positive, because a negative squared can be a positive number. On the bottom, I'm going to get a negative, and positive divided by negative is minus infinity. So if all we wanted to know is, does that limit exist? Our answer is no. The limits do not exist. And we know that as we're going to the right, positive infinity, we're going up. And as we're going to the left, we're going down. So no matter what this function looks like, at the ends, we're going to see this. So I'm just going to put a little box here, meaning something happens with our function. But the end behavior is definitely growing without bound as I go to the right, and dropping without bound as I go to the left. So that's an easy enough question to answer, just by looking at those leading terms and what happens to those in terms of their signs. But that's not enough. We can actually tell a lot more, and what we're going to be able to tell, let me show you by drawing the graph. It looked like, Ollie, it looked like you were about to ask me a question.
Yeah, just to clarify that, like algebra rule with rational functions about the degree on the top and bottom, that does not apply to like x to the 1/2. Is that right?
No, it would. It absolutely would. So like if we had, say, an x to the 1/2 on the bottom, then the same thing would happen. You look at the degree on top is 2, the degree on the bottom is 1/2, and you'd still have the same issue. Or if the top, let's say, was just a 3x to the 1/2 over x minus 1, then we go, oh, the degree on top is smaller than that on the bottom. So you actually,
yeah, sorry, go ahead.
no, I was going to say, so you can do the same sort of trick when you have fractional exponents.
So that example that you did before of x over the square root of 9x squared plus 4, would it not apply in that case just because it's not just x to the 1/2, because there's a bunch of other things in there too?
Correct.
Okay.
Because there was addition inside of that square root.
Okay, gotcha.
Had you not had the plus 4, if it was just like 9 square root of 9x squared, then we could have done the same trick that we did here.
Okay, great, thank you.
You're welcome. All right, so let me share my screen because I want to go ahead and show you what the graph of this thing looks like. So we're going to go back to Desmos. I'm going to turn off all the other stuff that we've drawn so far. But let's go ahead and put this function in. So we've got 3x squared plus x plus 1 divided by x minus 1. Let me zoom out here just a touch. Okay, so this is what that graph looks like. So hopefully you see it here in blue. And you can definitely see the infinity. You can see that as we go to the right, this thing just keeps growing. And you can see that as we go to the left, it keeps dropping. So we're definitely seeing that. But what I want you to notice is that this is starting to look like a line when we get far away from the center. Right? When we get far away from here, it's starting to look linear. In fact, if I zoom out a little bit more, do you agree that looks like a line? I hope so,
Yes.
because it definitely looks like a line to me. All right, so this one, it actually looks like it's becoming a line or getting really close to a line when we start moving far away. So that means it has an asymptote. It's just this asymptote isn't vertical and it isn't horizontal. It's off at a slant. Well, let's see if we can go find it. So I'm going to pop back here to the whiteboard. All right, so it definitely looks like there's an asymptote. And this type of asymptote, it goes by two different names. Sometimes it's called a slant asymptote, but the technical name is what we call an oblique asymptote. And so I'm just going to write here, this is a slanted asymptote. Okay, still a line that we approach. It's just not horizontal or vertical. Now, we definitely saw that with this function. And I'll even tell you when it happens. Okay, these things occur when the degree on top is one more than the degree on the bottom. And that's what we saw here. The degree on top was 2. The degree on the bottom was 1. And because it's 1 different, that means that we're going to get an oblique or a slant asymptote. So when you're in that situation, look for these, because they can help you figure out what the graph looks like. They give you more information, basically. Okay, so the question is, how do we find them? Don't shoot the messenger. We're going to find these by doing long division. I heard all of your groans, by the way, even though all your mics are muted. I heard that. We're going to do long division, and not just long division, we're going to do polynomial long division. Ugh. Okay, but polynomial long division is actually going to get us those slant asymptotes. So it's probably been a while. Let me remind you about polynomial long division. We'll do it with this guy. All right, so here's our setup. When we want to do the polynomial long division, we're going to, just like any long division, you're going to put what we're dividing on the inside. So the 3x squared plus x plus 1 is what we're dividing into. And we're dividing by the x minus 1, so we're going to put that on the outside. And the process here is to begin with the highest degree terms and figure out what do we have to multiply to the one on the outside to get the one on the inside. So to get 3x squared from an x, I need to multiply by 3x. I'm lining it up so that all of my degree terms are in columns. That's why I put that over here above the x. All right, so now what we do is we multiply. So we get 3x squared minus 3x. And now we subtract it. And this is the process for long division, even with numbers, right? Figure out what goes in, you multiply, and then subtract off. So this is going to give us 3x squared minus 3x squared is 0. 1x minus a negative 3x is 4x. So now we bring that 1 down, and now what we have inside is 4x plus 1. But now we're going to do the same thing. We're going to look at these leading terms and figure out what do I multiply to x to get 4x. And the answer to that is 4. So you do that multiplication, you get 4x minus 4. We subtract it off. 1 minus negative 4 is a 5. So 1 plus 4 is 5. And at this point, we stop because the degree of what's inside is less than the degree what we're dividing by. So in essence, what we just did, so we took this 3x squared plus x plus 1 over x minus 1. It's actually equal to 3x plus 4 plus 5 over x minus 1. All right, so Ollie just asked, is this different than synthetic division? This specific one, no. This specific one you can do with synthetic division. However, synthetic division only works when your denominator is linear. If it's just x plus or minus a number. If that bottom had been in a cubic, let's say, then synthetic division won't work. So synthetic division is great in this case, like for this specific one. The long division is more robust, and we're going to need it if the bottom isn't linear. But yeah, synthetic division gets you to the same place. All right, so doing this division brought us to this point. Now, here's what I want you to notice. Look at this last piece, the 5 over x minus 1. Right, that was the part that came from the remainder. This is going to go away. I'm just going to write here that this goes to 0. As x gets big, 5 over x minus 1 is going to go away. It becomes less and less important. So as we keep moving further away, this little chunk disappears, and our function starts looking like 3x plus 4. Well, there's your slant asymptote. That line that this function was approaching was the line y equals 3x plus 4. So that's our oblique asymptote. So I want to go back to Desmos just to show you. I want to draw the graph of y equals 3x plus 4. We'll put it on there with the other one. So you can see that that is what we're approaching. So I'll go ahead and share that back again. All right, so you guys can all see Desmos. Let me zoom back out, or zoom back in here. So there's our original function. Let me throw in a line here. So we have y equals 3x plus 4. Okay, so there's our green line, the y equals 3x plus 4. And you can already see a little bit, if we come down here, how those functions are starting to approach each other. right? You can see that a bit. But when I start zooming out, you'll definitely see it. Now, like getting down here, seeing a difference between the green and the blue, it's pretty non-existent, and the same thing up here. And if I zoom out even further, remember back when it started looking like a line? Tell me the difference between the green and the blue. And you can't. You literally can't see a difference. And that's because once we get out to these kind of numbers, I mean, think about the numbers we're plugging in here. We're plugging in 100, 200, and things like that. Think about plugging 100 into that factored form or into that division form with that remainder piece, 5 over 100 minus 1. So 5 over 99, that's roughly 0.05. That's tiny. That's a tiny amount that we're adding. So it kind of disappears. All right, well, so these are oblique asymptotes. These are slant asymptotes. And really just take them for what they are. They are lines that we're approaching. They're lines that our function approaching. It's just now they're not horizontal or vertical. They're off at some angle. All right, so they occur when the top is one more, when the degree on top is one more than the bottom. That's how you know when to look for them. And we're going to use that. We're going to use that to help us draw graphs next time. All right, so I know that we have a little bit more time today, but I'm going to stop because I don't want to actually get into the putting this all together. But what we'll do next time, what we'll do on Friday, no quiz, by the way. There is no quiz since this was a weird week with the day off. We're not going to have a quiz on Friday, so it'll just be usual class. But we'll put all this together. We'll put this infinite limit stuff we just talked about today, add it to the first derivative stuff, increasing, decreasing, and extrema, and the second derivative stuff, concave up, concave down, inflection points. We're going to put that all together with some other stuff you know from algebra, and we're going to draw some really, really strong kick-ass graphs. We're going to take functions that we have no idea what they look like, but we're going to apply these techniques to get spot-on pictures, right? And you're already starting to see that we're getting pretty good at it with some of the other ones that we've done before. But after Friday, you should be convinced that you have all the tools you'll ever need to draw the graphs of functions. You'll never need a graphing calculator again if you're willing to do a little calculus. So that's what we're going to do on Friday. I guess other than that, I've got nothing else. So unless you guys have any questions, we'll go ahead and call it a day. All right, well, hearing none and seeing none, we'll go ahead and stop recording.